In this example, we're going to focus on finding the domain of various functions. And recall that the domain of a function is a set of all inputs that are actually allowed to put in your function without receiving some kind of major error. So throughout this course, we're going to be investigating functions that are defined on the real number line. So we want to make sure that the domain of our function is a set of real numbers that's actually allowed in the function. And here's what I mean by allowed. Okay, there's two things in the real number system that are not defined, right? So they're undefined is what we call them. And those two things are division by 0 and even roots of negative numbers. All right. So these are the two things that you really have to look out for when you're finding the domain of a function. These two things are not allowed, they're undefined, they are not viable values, okay? So the domain of each of these functions is going to start out as being the set of all real numbers, and then we're going to eliminate any values that cause us to divide by 0, or any numbers that cause us to take even roots of negative numbers. So when we're looking at division by 0 as a possibility, chances are you have some expression over some other expression, and we can't let the denominator equal 0. So our strategy for this is that the denominator, in this case q of x, cannot be 0. We're going to set up this non-equation and solve it. This will tell us the bad x values. Even roots of negative numbers are not allowed, so you have some kind of even index on your radical and you have some kind of expression inside. So the way that we say not negative in mathematics is by using an inequality. So what you're going to do for this situation is take the expression inside of your radical and set it greater than or equal to 0, and that will ensure that it's not negative. You'll solve this inequality and that'll tell you viable x values. So we're going to apply these in our examples. So for part A, I have f of x defined as x divided by x squared minus 16. So you notice I actually have a fraction, so I'm going to consider division by 0. You can see that there are no radicals in this expression at all, and definitely no radicals with an even index. Therefore, number 2 is not going to occur. So, first thing I notice is that the denominator of this function can actually be factored because it's a difference of squares. So the denominator can't be 0 because I cannot divide by 0. So what I will do is take the entire denominator as is. Do not cancel anything if you can. You want to take the entire denominator and set it not equal to 0. Okay, because it can't be 0. And the way you solve a not equal to equation is the same way you solve an equal to equation. So you see I have a product equal to 0, so I can use the 0 product rule and set each factor not equal to 0. Solve for x, and I find that x can't be 4 or negative 4. So the domain of this function is every real number except 4 and negative 4. So we could write this using set builder notation. So all of the x's such that x is not 4 or negative 4. In part B over here, I have g of x defined to be the square root of 3x minus 12. So first thing you notice is that there is no fraction, there is no denominator, which means division by 0 is not going to occur, so I don't even need to consider it. However, I do have an even root here. Since this is a square root, it has index 2, so number 2 is quite possible. So what I need to do is take the expression inside this even root, and this is not allowed to be negative, which means it has to be 0 or bigger. So I'm going to solve this inequality for x. So I will add 12 to both sides, divide both sides by 3, and this tells me that my x values have to be 4 or bigger to be in the domain. So I could maybe in this example, I'll sketch the domain on the real number line. Here's the number 4. So x is allowed to be 4, so it gets a nice closed circle because of that or equal to, and then it also has to be bigger. Great. So I have 2 more parts to this problem. I have parts C and D. Part C, I have h of x equals 4 divided by the square root of x minus 9. So you can see that I put both cases in here. I have a fraction and an even root. So I have to consider both of these options. So you'll notice that the square root is in the denominator. So first and foremost, that denominator cannot be 0. So I take the denominator exactly as is. It's got this square root quantity, right? What's the square root of 0? 0. So essentially, x minus 9 can't be 0. So I'll add 9 to both sides, and we see that x cannot be 9. So I already know that I have one x value that's not allowed. However, that only takes care of the fact that this is in the denominator. I also need to take care of the fact that this is a radical with an even root. So the second thing I'm going to do is take the quantity inside my radical and set it greater than or equal to 0, because it needs to be positive. So I'll solve this inequality by adding 9 to both sides, and I can see that x needs to be greater than or equal to 9. Now notice, x is not allowed to be 9, but down here I'm saying it is. So what I need to do to find the domain of this function is I actually need to intersect these two sets right here, everything except 9 versus everything bigger than 9, including 9. So what we end up getting for this example, if I sketch each of these on the number line, is this says everything except 9, and this says 9 or bigger. If I intersect these two sets, you see that the domain is actually only numbers larger than 9. Okay, this 9 is shaded here but not here. Since it's not shaded in both sets, it is not included here. So the domain in this example is only x values larger than 9. Okay, last example, part D, j of x equals 5x plus 2. There are no fractions, so there's no worry of division of 0. And there are no even roots of anything, no square roots or fourth roots, etc. So you can see that we will not violate either of those two rules. In fact, this is a nice linear function. It's well-defined and easy to graph. So the domain of this function is going to be all real numbers, negative infinity to positive infinity, because there are no bad x values.